Students, today our lecture is about addition and subtraction of assigned numbers. So before entering to the topic, first we need to know how to write a binary equivalent of any decimal numbers. Here we have three examples. I think everybody know how to calculate the binary equivalent. So here for 17, to calculate a binary equivalent, we must divide it with 2. So 2 8s 16, the remainder is 1. 2 4s 8, remainder is 0. 2 2s, remainder is 4. 2 1s 2, remainder is 0. So we keep on dividing a number till we get 0 or 1, and we get the binary equivalent. So we write it from the bottom to top, 1 0 0 1 0 1. So this is the binary equivalent of decimal number 17. Here we have two more examples. 138 can be derived. We can also write a binary equivalent of 138 in the same fashion. So 0 1 0 0 0 1 0 1 0. This is the binary equivalent of 138, and 100 can be also written in the same fashion. So this is about the positive numbers representation in a binary format. But how to represent a negative numbers? We have three different ways of representing a negative numbers. One is signed magnitude representation, one's complement representation, and two's complement representation. Out of these three, the computer will mostly use two's complement representation for a negative numbers. Suppose to calculate a negative value of any number, first we need to convert that number into binary equivalent. Is having a sign bit, the most significant bit is used as a sign bit. 0 represents positive value, 1 represents negative value. To convert this into in a negative form, so we have to complement this. We need to write 1's complement and we need to add plus 1 to the 1's complement value. So we can get the 1's complement by inverting each bit value in original binary value. So 0 can be written as 1 and 1 can be written as 0, and 1 0 1 0. For a 0 we write 1, for 1 we write 0, for 1 we write 0. So like this we can generate 1's complement. So we get the 2's complement by adding a 1 to the least significant bit of a 1's complement. So we wrote the same 1's complement value here. We added 1 to the least significant bit. So we'll get 2's complement. 1 and 1, 1 0. 0 here, carry 1 here. 1 plus 0, 1. And remaining all bits are just copied like this. So this is a positive value, and its 2's complement negative value is this one. So in the same way, for if we have given negative value, to calculate its positive value, we just 2's complement the negative value, will get the positive value again. So you get more examples. So plus 5. So the number of bits to be represented for a 5 is your choice, because a number can be represented using 32 bits in our register. To make our problem simple, we may use any number of bits. So if the question is, if they represent how many number of bits to be, if they mention how many number of bits to be represented, you use that many number of bits in your number representation. Otherwise you can just use 0 1 0 1, only 3 bits for representing a 5 and 1 bit for sign 0 1 0 1. So here in this example they have used 8 bits for representing a 5. So to calculate a minus 5, we'll just use 2's complement value. 1's complement, inverting each bit in a register 5 and adding 1 to the least significant bit. So we'll get the 1. So 5 value is this one and minus 5 value is this one. So from minus 5 also you can get that plus 5 value by just 2's complementing this. And we have one more example, 13. 13's 1's complement plus 1 you will get the plus 13. సో మైనస్ 13 నుంచి ప్లస్ 13 కూడా తీసుకొని రావచ్చు. సో హియర్ వీ హ్యావ్ వన్ మోర్ ఎగ్జాంపుల్ విచ్ హ్యాస్ more than 10 bits in the register. So this is the binary equivalent of 10 is actually 1010. So all the remaining bits of a register could be 0. Then its negative value can be written by complementing the value and adding 1. So adding 1 means it adds all zeros to the remaining bit positions. So you'll get negative 10 value. Of calculating 1's complement and 2's complement, we can simply write the 2's complement value by this logic. So we keep on tracing the 1 from the right side of a number. Suppose we have a 34 value is 0 1 0 0 0 1 0. So last bit is a sign bit. So we can directly write the 2's complement negative 34 by knowing this number. You trace the number from right side. So whenever you reach the one from the right side, so up to that you can just copy the values 0 and 1. After you reach 1, all the remaining digits can be inverted to get the negative value. So 1 becomes 0, becomes 1, 0 becomes 1, 0 becomes 1, and 1 becomes 0, and 0 becomes 1, 0 becomes 1. So this is the way of calculating the negative value without converting this into a 1's complement and adding a 1. Even you do 1's complement adding 1, you will get the same results. So generally for addition of any numbers we have, so in just like in a decimal number, for adding a two numbers we add the digits of 1's position and 10's position, 100's position individually. In the similar way we can also add the digits of a binary number in bit positions. So generally for if you add 0 and 0 you'll get 0. If you add 1 and 0 you'll get 1. If you add 0 and 1 you'll get 1. If you add 1 and 1, so generally it is 2. So 2's binary equivalent is 1 0. So 0 will be the sum value, carry is the 1. So there is sometimes a possibility we add the three numbers 1 1 1. So if we add the three numbers, what is a decimal equivalent is 3. 3's binary value is 1 1. So 1 comes in this position and the carry will be forward to the next bit. So we have several additions here. So if you want to add plus 2 value with plus 3, so plus 2's equivalent is 0 for a sign bit. 2 value is, suppose in all these examples they have taken 4-bit register. So plus 2 can be written 0 0 1 0. Plus 3 can be written 0 0 1 1. So addition can be performed by adding each bit. 0 plus 1 is 1. 1 plus 1 is 1 0. 0 here, carry forward to the next bit. 1 plus 0 plus 0 is 1. 0 plus 0 is 0. So you will get 5 value. So here we have a second example 0 1 0 0, which is performing minus 6 value. How to get the minus 6 value? You write the plus 6 value in 4 digits and complement. So the complement of plus 6 is 1 0 1 0. You just simply add. So in binary additions, both addition and subtraction can be done in the same fashion. For addition and subtraction we add the digits, no subtraction performed by the computer. It will just add the number. So if the minus sign is present, we will just 2's complement the value. So minus 6 value is calculated by 2's complement in the 6 and we'll just add. So that is what happened. So in first 4 examples they just used addition of two numbers. For a minus value they used complemented value of plus value. These four are about addition. For a minus operations, so we'll minus 7 and minus 3 and minus 7. So binary equivalent of minus 3 is 1 1 0 1. Minus 7 is 1 0 0 1. So what is the symbol here? They are going to perform subtraction. So subtraction is not possible in a binary computers. So we have to convert the second digit into a positive value by writing its 2's complement value. So the 2's complement of 1001 is 0111. So we have converted this into 2's complement format, and this minus symbol is become plus here. So we'll just add two numbers. So wherever we encounter a minus symbol, we'll just 2's complement and addition is only performed. So here we have second example, plus 4. Plus 4 value is 0100. So this entire 4 digits are 2's complemented and the minus symbol will become plus, and then we add the two numbers. So wherever you will have minus, you will just 2's complement the value. So this is what happened in all the examples. Next, so generally we'll be having to calculate any number, we'll be having organ. This x is called organ and y is called add end. So suppose in this example they have taken organ as 7 and odd end as 6. 7's binary equivalent is 0 1 1 1 and 6 binary equivalent is 0 1 1 0. So how it happens, we'll keep on adding each bit in each position. 1 plus 0 is 1. So carry generated in this is 0. So that is forward to the next bit. 1 plus 0 plus 1 plus 1 plus 0 is 1 0. So 0 here, carry is forward to the next bit. 1 plus 1 plus 1 is 1 1. 1 here and carry 1 here. And 0 plus 0 plus 1 is 1 and carry is 0. So this is how the the computer will generate addition of a binary numbers. So what is happening in the each bit position? It is calculating a bit of x and a bit of y and adding a carry in that is generated from the previous bit. After adding these three, you will get some value and a carry out of the carry out that is forward to the next bit. So this is actual what happens. So this entire action is performed by a full adder. A full adder is a circuit which has two input bits and one carry bit. So this full adder, this addition of these three bits are calculated or performed or implemented by using this simple circuit. It has inputs A, B and carry in our example xi, yi and ci, and output it will generate is some bit and carry bit. It is not entire number of bits, it's a single bit. A full adder can add 3 bits and it generate 2 bits. So this is possibilities. How many inputs we have? 1 2 3 inputs, xi, yi and ci. So what are the different combinations? 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So these are the possible input values. So now what will be the outputs? For 0 0 0, 0 plus 0 plus 0 is sum is 0. So what will be the carry? Carry is 0. For 0 plus 0 plus 1, what is the sum? Sum is 1 and carry will be 0. For 0 plus 1 plus 0, sum is 1, carry will be 0. For 0 plus 1 plus 1, the sum will be 1 0. So means 0 comes here, carry bit will be 1. For 1 0 0, the sum will be 1, carry will be 0. And for 1 and 1, the sum will be 0 and carry will be 1. So for in the similar way, for a triple 1, the sum will be 1, carry will be 1. So we'll get the formula for sum value Si. When Si is 1, Si is 1 when Xi is 0, Yi is 0 and Ci is 1. So Xi bar, Yi bar and Ci. And when it is 1 again, it is 1 again when Xi is 0, Yi is 1 and Ci is 0. Xi bar I bar plus into Yi into Ci bar. And again when it is 1, when Xi is 1, Yi is 0, Ci is 0. Xi into Yi bar, Ci bar. Here bar represents a 0 value. Again this sum is 1 when Xi is 1, Yi is 1, Ci is 1. Xi, Yi, Ci. So by simplifying this equation, we'll get Xi is XOR of Yi XOR of Ci. So after simplification, we'll get this value. So again in the similar way, we can write the formula for Ci plus 1. Carry at I plus 1 position. It is 1 when Xi by Xi bar plus Yi plus Ei. And when Xi and Yi bar and Ci. And at Xi, Yi and Ci bar and Xi, Yi, Ci. So after simplification, we'll get Xi into Ci plus Xi into Yi into Ci, Xi into Ci plus Xi into Yi. So this is how we can calculate the truth table and Boolean expression for the sum and carry values. So from this Boolean expression, we can derive the gates. So what is SI value? SI value is Xi XOR, Yi XOR, Ci XOR. So we have a simple XOR gate here. So the input of this XOR gate is Xi, Yi and Ci. Xi, Yi and Ci, and output is Si. How to get Ci plus 1? Ci plus 1 is Xi into Ci, Yi into Ci, Yi into Ci. So and between Yi and Ci, and gate, and Xi and Ci, and gate between Xi and Ci, and gate between Xi and Yi, and addition of all the three products. So all the products are added through the OR gate, 3 AND gates and 1 OR gate. So these two circuits are part of this full adder. So what are the inputs? Xi, Yi and Ci. Outputs are Si and Ci plus 1. So this simple full adder will only add a single bit of Xi, Yi and Ci. Then if I have 32-bit register, how many full adders I require? I require 32 full adders. So that is why we can connect all the full adders like this. So full adder at 0th position, full adder at 1st position, and so on. Full adder at 31st position. So we can calculate the sum of the two registers by having n different full adders. So this type of connecting one full adder to another full adder is called n-bit ripple carry adder. So this entire circuit will add two registers. Next, if you want to add more than one register, we use cascade of n-bit adders. Like want to have multiple addition register, we use cascade of n-bit adders. Sometimes when we calculate the addition of two numbers, the addition may exceed the capacity of the register. So that is calculated, that is known by the computer through this logic, so which is called overflows. So if overflow is happened, we should not neglect the carry bit. So carry bit has to be included as part of the answer. So that is known by the system by using this circuit. X overflow can be calculated through this formula. X value at n minus 1 position, y value at n minus position into S bar value at n minus position. If these two have same sign and sign has a different, then you can treat that as a overflow, or x and y has 0 negative sign and sign bit is positive, then also you can understand that there is overflow occurred. Or so you can also calculate whether there is overflow or not by using carry XOR operation between carry at nth position, carry at n minus 1 position. So this is a circuit which is capable of doing both addition and subtraction. So generally the computer can perform addition and subtraction in the same way. So here, so what I have to do, I need to have n bit adder for adding n bits of x and n bits of y. For addition, so this circuit will perform both addition and subtraction. So if you want to, if this has to perform addition, the adder control stop has to be given 0. So when this is 0, so it will add, suppose xi, it will add x0 and y0 plus carry 0. So it will just perform y x0 plus y0 plus 0, means it is performing addition. So when add or subtract control is given as a 1, if it is 1, so whenever there is a input 1 to the XOR gate, it will complement the second input. So whatever the value of x will be complemented out of the XOR gate. So if it is passed as 1 here, then output of this XOR gate is y bar. So this adder will perform x0 plus y0 bar, and the carry that is again added to the first bit of adder control strobe is 1. So it means it is perform x0 plus y bar plus 1, which is nothing but 2's complement of y second value. So it is performing subtraction. So this is how the circuit will be used both for addition and subtraction. Thank you.